Today, I'm going to take you on a journey back to the 17th and 18th centuries to explore an intriguing yet largely forgotten theory of gravity, Lesage's kinetic model. Most of us are familiar with Isaac Newton's law of universal gravitation. But did you know there was another competing idea at the time? That's right. Nicolas Fatio first proposed this alternative in 1690. In simple terms, Lesage's kinetic theory of gravity suggests that invisible, tiny particles, which he called ultramundane corpuscles, are constantly streaming through space from all directions. According to Lesage, these corpuscles impact all material objects, such as planets, stars, and even you and me from every possible direction. Now here's the interesting part. When two objects are close to each other, they partially shield each other from these incoming corpuscles. This shielding effect means fewer corpuscles hit the sides of the objects facing each other, creating a net pressure that pushes the objects closer together. This mechanical explanation was Lesage's attempt to provide a more intuitive understanding of how gravity works, as opposed to Newton's rather abstract force at a distance concept. But despite its creativity, the theory never gained widespread acceptance. Why? First off, there were some significant issues with the theory. One major problem was the amount of energy these corpuscles would need to transfer to objects to produce the observed gravitational effects. According to the theory, the energy imparted should cause objects to heat up considerably, which we don't observe in reality. Additionally, the theory failed to account for certain gravitational behaviors accurately, especially on astronomical scales. Particularly with the development of Einstein's theory of general relativity, Lesage's model faded into obscurity. Nevertheless, Lesage's kinetic theory of gravity remains a fascinating chapter in the history of science. But why shouldn't we explore? Imagine we have a single object, let's call it Object A, floating in space. According to Lesage, this object is being bombarded from all directions by tiny high-speed particles, which he called corpuscles. These corpuscles are evenly distributed, so Object A experiences an equal force from all directions, resulting in no net directional force. But what happens when we introduce a second object, Object B, nearby? Object B acts as a shield, intercepting some of the corpuscles that would have struck Object A from its direction. Similarly, Object A shields Object B. This means both objects are struck by fewer corpuscles on the sides facing each other, creating an imbalance. This imbalance results in a net pressure that pushes the objects towards each other, making it seem as though they are attracting. Let's consider the nature of these collisions. If the collisions between the corpuscles and the objects were perfectly elastic, meaning the corpuscles bounce back with the same energy they hit with, there would be no net directional force. However, Lesage proposed that these collisions are not fully elastic. The corpuscles lose some momentum when they hit the objects, meaning the reflected particles have less energy than the incoming ones. This results in a net force pushing the objects together. Finally, let's visualize the inverse square law. Imagine a massive object in space. The intensity of the corpuscles hitting this object is greater than the intensity of the corpuscles leaving it due to absorption or slowing down of the particles. If we draw a spherical surface around this object, the momentum imbalance per unit area decreases inversely as the square of the distance from the object. This is why the gravitational force weakens with distance. By breaking down Lesage's kinetic theory into these visual steps, we can better understand the mechanics behind his idea of gravity. Even though this theory has its flaws and isn't widely accepted today, it was a hope into the creative minds of early scientists. Lesage discussed the theory in great detail, and he proposed quantitative estimates for some of the theory's parameters. He called the gravitational particles ultramundane corpuscles because he supposed them to originate beyond our known universe. The distribution of the ultramundane flux is isotropic, and the laws of its propagation are very similar to that of light. Lesage argued that no gravitational force would arise if the matter-particle collisions are perfectly elastic, so he proposed that the particles and the basic constituents of matter are absolutely hard, and asserted that this implies a complicated form of interaction, completely inelastic in the direction normal to the surface of the ordinary matter, and perfectly elastic in the direction tangential to the surface. He then commented that this implies the mean speed of scattered particles is 2/3 of their incident speed. To avoid inelastic collisions between the particles, he supposed that their diameter is very small relative to their mutual distance. That resistance of the flux is proportional to uv, where v is the velocity of the particles and u that of gross matter, and gravity is proportional to v square, so the ratio resistance-gravity can be made arbitrarily small by increasing v. Lesage also attempted to use the shadowing mechanism to account for the forces of cohesion and for forces of different strengths by positing the existence of multiple species of ultramundane corpuscles of different sizes. Lesage said that he was the first one who drew all consequences from the theory, and also Prevost said that Lesage's theory was more developed than Fatio's theory. In the grand scientific discourse, no theory is immune to scrutiny. One of the most notable critiques of Lesage's kinetic theory of gravitation came from the illustrious James Clerk Maxwell. In 1875, Maxwell published a review of the Kelvin-Lesage theory in the 9th edition of the Encyclopaedia Britannica under the title Atom. With a touch of sarcasm, Maxwell wrote, "Here, then, seems to be a path leading towards an explanation of the law of gravitation, which, if it can be shown to be in other respects consistent with facts, may turn out to be a royal road into the very arcana of science." Maxwell dissected Kelvin's suggestion that gravitational particles possess different energy modes, implying that these particles are complex systems with their own internal energies. He pointed out that this notion required these particles to be held together by unexplained forces of attraction. According to Maxwell, such complexity would lead to a scenario where the temperature of ordinary matter would rapidly escalate, resulting in incineration within moments due to the bombardment by these hypothetical particles. Maxwell's critique didn't stop there. He argued that the theory necessitated an enormous expenditure of external power, thereby violating the fundamental principle of energy conservation. This pointed out a glaring flaw in the theory, as it conflicted with the established laws of physics. Preston, in response, argued that the kinetic energy of each individual particle could be minimized by assuming a sufficiently low mass and higher number density of these particles. However, this rebuttal didn't fully address the thermodynamic issues raised by Maxwell. Among these pioneering thinkers was Hendrik Antoon Lorentz. In 1900, Lorentz, a prominent physicist known for his work on electromagnetism and the electron theory, examined Lesage's model through the lens of his time's scientific advancements. Lorentz noted that Lesage's particle model was inconsistent with the electron theory, which was gaining traction. However, he proposed an intriguing alternative, substituting electromagnetic radiation for Lesage's hypothetical particles. Lorentz considered that trains of electromagnetic waves capable of exerting pressure might replace the gravitational particles. The discovery of X-rays, known for their penetrating power, further fueled this idea. Lorentz suggested that even more penetrating radiation than X-rays could exist, potentially explaining gravitational attraction. Despite this innovative approach, Lorentz identified a critical flaw. He demonstrated that an attractive force between charged particles, akin to the elementary subunits of matter, would only arise if the incident energy were entirely absorbed. This issue mirrored the fundamental problem that plagued the particle models. Lorentz stated, "The circumstance, however, that this attraction could only exist if electromagnetic energy were continually disappearing is so serious a difficulty that this cannot be considered as furnishing an explanation of gravitation." Additionally, Lorentz pointed out that if gravitational attraction were due to vibrations crossing the ether at the speed of light, the motion of celestial bodies would significantly alter this attraction. This contradicted astronomical observations, further undermining the theory. In 1922, Lorentz revisited the topic, examining Martin Knudsen's research on rarefied gases. He summarized his electromagnetic Lesage model, but reaffirmed his earlier conclusion. Without absorption, no gravitational effect could be produced. The re-examination of Lesage's theory identified several closely interconnected problems, such as excessive heating, frictional drag, shielding, and gravitational aberration. These issues significantly undermined the theory's viability. The recognition of these problems, coupled with a broader scientific shift away from mechanical-based theories, led to a progressive loss of interest in Lesage's kinetic theory of gravitation. By the dawn of the 20th century, Lesage's theory had been largely eclipsed by the rise of Einstein's theory of general relativity. In 1965, the renowned physicist Richard Feynman revisited the Fatio-Lesage mechanism, primarily as an example of an attempt to explain a complicated physical law, specifically Newton's inverse square law of gravity, using simpler, primitive operations without complex mathematics. Feynman noted that while the mechanism of bouncing particles does reproduce the inverse square force law, it ultimately does not work because of the drag it predicts for moving bodies. Feynman's analysis serves as a poignant reminder of the limitations and evolving nature of scientific theory. In addition to its gravitational implications, Lesage's theory has inspired various non-gravitational applications and analogies. One such concept is mock gravity. In 1941, Lyman Spitzer calculated that the absorption of radiation between two dust particles leads to a net attractive force proportional to 1 divided by r square, though he was unaware of Lesage's shadow mechanism and Lorentz's considerations on radiation pressure and gravity. Later, in 1949, George Gamow proposed that after the Big Bang, the temperature of electrons dropped faster than the temperature of background radiation. This led to a Lesage-like mechanism between electrons, potentially playing a role in galaxy formation. However, this idea was disproved by Field in 1971, who showed that the effect was too small due to near-thermal equilibrium between electrons and background radiation. In 1986, Hogan and White revisited the concept, suggesting that mock gravity might have influenced galaxy formation via absorption of pregalactic starlight. Yet Wang and Field demonstrated that any form of mock gravity was insufficient to produce a significant force for galaxy formation. The Lesage mechanism also finds relevance in the behavior of dusty plasma. Another intriguing analogy is found in quantum field theory with the Casimir effect. Here, the existence of virtual particles leads to a net attractive force between two plates due to differences in vacuum energy densities.